easier, and then we can get started with it. Okay. So
Yes,
again,
because
yeah, go ahead.
so yeah, exactly because the third part, I didn't really get third part last time, and because it's pretty lengthy and there's a lot of content, so I still need you know more explanation related to the third part and how we dissect it and answer it.
Sure, sure, no problem. Okay, in fact,
Yes, sir.
okay, so really the first two parts are pretty simple and straightforward since they require you to go with the formula. So in part one, we understand that the number of moles, I'm not going to do part one over here instead. Better if I write part one over here. So in part one, moles of H2SO4 are something that we supposed to find. So in case of H2SO4, we have 20.0 cubic centimeter of the sulfuric acid, and the concentration is 0.30. We need to divide this volume by 1,000 to convert it into decimeter cube. We multiply it with concentration and we really get the number of moles, the answer to which is 6 into 10 raised to the power minus 3 moles. Okay? And for part 2, we need moles of NaOH. And in case of NaOH, we have the information based on that we have 40.0 cubic centimeter of NaOH. It's actually 40, but for three significant figures, I can convert it into 40.0. And we are going to do the same with it, divide it by 1,000 to convert it into decimeter cube, multiply it with its own concentration, which is 0.20 mole per decimeter cube. And it gives us the answer to be 8 into 10 raised to power minus 3 moles. Okay, so that's the number of moles of H2SO4 and NaOH that we have. At the start of the experiment, we already have the balanced chemical equation as a part of the question. We do not need to work upon it anymore. So we can really get to step number 3. Now, the first ideology on which I am going to solve step number 3, method 1, let's call it, and it states that limiting reactant, and I'm going to mention it over here, that limiting reactant is something that I am going to mention as LR during my whole steps, and excess reactant, whatever that reactant is, we don't know for sure whether that one is H2SO4 or NaOH yet. We are yet to find it out. So I'm going to mention it as ER. So LR produces least number of moles of product. Whichever one is the limiting reactant is going to produce the least number of moles of product. So that's why this is the base point on which this straightforward method applies. And we understand the fact that since LR is going to give us least number of moles of product, what we do is that we take NaOH and we consider it with a ratio, and we can take ratio of any of our products. So I can either take water, I can take Na2SO4, but this time I'm going to go with Na2SO4. So in order to solve this question, I need to take the ratio side by side, and I'm also going to take the ratio of H2SO4 along with Na2SO4, right? So from the equation, 2 moles of NaOH give me 1 mole of Na2SO4. So since I have 8 into 10 raised to power minus 3 moles of NaOH, so how much I'm gonna get is going to be X. On the other hand, from the balanced chemical equation, I have 1 mole of H2SO4 that gives me 1 mole of Na2SO4. And since I have a total of 6 into 10 raised to power minus 3 moles of H2SO4, how many moles of Na2SO4 I'm going to get is going to be X. So X is equal to 8 into 10 raised to power minus 3 divided by 2. For my left-hand side, the answer would be 4 into 10 raised to power minus 3 moles. And for the same kind of calculation, x is equal to 6 into 10 raised to power minus 3 moles as a part of this calculation. This is simple ratio portion. Why do we go for ratio? That because this ratio gives us the idea that how many moles of product can we form if we completely use either one of the reactants, right?
Yes, sir.
Now, if you remember my previous example that I made about the sandwiches that you are going to make. So for that example, I hope you remember we calculated the number of sandwiches we can make from either the slices of bread we have or the ketchup sachets that we had or the patties that we had. And we had different answers in different perspectives. The bread slices told us we can make a maximum of 15 sandwiches. The patties told us we can make a maximum of 14 sandwiches. And again, the queso sachets told us that we can make a maximum of 15 sandwiches. But uh, in order to go with the actual answer, the least one is the correct one. So since we know it produces least number of moles of product, so the least one is going to be the correct one. So this is the correct answer, which proves this one is LR, limiting reactant. Since this is not the correct answer, it tells us this one, this reactant, is the excess reactant. So that's how we identify. And since we have two questions to answer in part three, the reagent in excess and the reason, so the reagent in excess would be H2SO4. Make sense?
Sir, could I write in the reason that with the method that we used, NaOH was the least, which was 4 times 10 to the power of minus 3 moles, compared to H2SO4, which gave us 6 times 10 to the power of minus 3, which concludes to NaOH being the um, uh, limiting reactant. Thus, the excess would be H2SO4. Would that be an appropriate reason?
Yeah, the whole reason is correct, except for one small part. The 4 into 10 raised to power minus 3 moles. Remember, these moles are calculated for Na2SO4. So make sure whenever you mention these number of moles, these are the number of moles that product form because of the consumption of NaOH. So just make sure whenever you mention 4 into 10 raised to power minus 3, these are the number of moles of Na2SO4 formed because of NaOH. Okay, the same goes for this one. These are the number of moles formed of Na2SO4 of the product when we completely use the reactant.
Or
Okay, makes
okay,
sense. The rest of the reasoning was perfectly all right.
so we don't really have to give a factual reason. We just have to uh put the method and what the method gave us.
No, no, no. Since you quoted 4 into 10 raised to power minus 3, that's why I said the reason is correct. Okay, when you're reasoning for this question, you need to mention a couple of values. Whether you mention 4 into 10 raised to power minus 3 moles of Na2SO4 formed because of NaOH, or you tend to mention that 6 into 10 raised to power minus 3 moles of Na2SO4 formed because of H2SO4, either one can give you the marks for the correct answer. Because excess reactant definitely makes more product, and limiting reactant definitely makes less number of moles of product. So you need to quote either one of the values. You may quote both, it's up to you. The rest of the reasoning is perfectly fine. And I said your reasoning is fine because in the start of your sentence, you quoted the value 4 into 10 raised to power minus 3 moles of Na2SO4. You just quoted 4 into 10 raised to power minus 3 moles. The point I was trying to make, you need to quote 4 into 10 raised to power minus 3 moles of Na2SO4 formed. That's about it. That's the only small change I wanted in your own answer.
Okay,
Make
sir.
sense?
Yes, sir.
Great, great. Now, apart from reasoning so far, what we can actually reason in a good way, or what the examiners sometimes tend to ask as a question, is that you quote the amount of excess reactant left unreacted. Okay. For these, we need to calculate the amount of H2SO4 consumed. And for that one, I actually went with the older method, the next step of the method one I did last time. And that was actually confusing. So far, what we have done so far can only get you to identify the limiting or excess reactant. Okay. Well, we can always go with another method. So I'm going to explain another method, what we call a more sophisticated method on the right-hand side. So let's go for method two for the same explanation. Now, method one and method two both tend to identify either the limiting or the excess reactant for us. Method two is really simple and straightforward. Method two implies that if we're going to use either one of the reactants completely, all of their moles, the other reactant that we require is either going to tell us the excess reactant or the amount of the limiting reactant. So what you need to do in method number two actually wants you to not go with multiple ratios at the same time. See, in method number one, if I highlight, you went on with this ratio as well as this ratio at the same time. So actually, method number one required you to go with two ratios at the same time. Method number two does not ask you to do so. So it's pretty simple and straightforward. Method number two wants you to go with reactant one ratio reactant two side by side in just one ratio. So let's assume reactant 1 is NaOH since that's written first in the equation. Reactant 2 is H2S4 because that's written second in the equation. Right? Makes sense so far?
Yes, sir.
So since the equation says we need 2 moles of NaOH to react with 1 mole of H2S4 to produce our product, since number of moles of NaOH are, and I'm going to put that as a hint, NaOH are these. So we are supposed to use this value over here. So this means 8 into 10 raised to power minus 3. What are these moles going to use? X. Now, this gives me a great idea that X would be equal to 8 into 10 raised to power minus 3, which we're going to divide by 2, which gives us the answer 4 into 10 raised to power minus 3 moles of H2SO4 used. Now, that's a great way to do it. This step alone actually gave me many answers than just one. Okay. Now, let me explain this step because this step is more sophisticated, hence a little bit more complicated. This might seem as a simple ratio, but this ratio is giving us way too many answers in a single step. Let me clarify how. Now, this step clearly tells you that you used the complete amount of NaOH you had in the start of the experiment. By using the complete amount of NaOH, you clearly used less than what you had for H2SO4. How? Notice, you had 6 into 10 raised to power minus 3 moles of H2SO4, but you used only 4 out of those. So that means H2SO4 is an excess reactant. So this one is definitely ER because you have already consumed all of your NaOH. So this one is LR. Why limiting reactant? Because you have completely used it. Why excess reactant? Because you started off with 6 into 10 raised to power minus 3 moles. You only used 4 out of it, and you are still left with some amount of it, which clearly gives us the idea that 6 into 10 raised to power minus 3 was the total amount, and we only used out of it 4 into 10 raised to the power minus 3, which is the consumed amount, right? And the amount left unreacted would be the answer of this subtraction, and that is 2 into 10 raised to the power minus 3 moles of H2SO4. So this single step actually solved a whole lot of problems for us as compared to the two ratio steps in the method number one. So method two is actually more sophisticated, but answers a lot more questions in a single step. But again, to pick up the whole sophistication of method number two, you must be good at solving the questions with method number one as a prerequisite. So it's entirely up to you which method you want to go with. Let me tell you, method number one is not complete yet. We still have two more steps to go with until we get to what we have done in method number two. I mean, the calculation of the left unreacted amount of H2SO4, because we are not going to consume all of the H2SO4 that we have for this question. And definitely there would be some amount that would left unreacted by the end of the experiment. And to calculate that amount, we need to go with some questions. Yeah, that is what we are supposed to do. So which one do you find easier? Let's be honest.
Sir, so there aren't any other steps, right? In method number one. This this is
Yes,
it.
method number one actually has more steps. So let's go with those steps. So right after identifying ER and LR, you need to go with a ratio. So what you do is that you take the ratio of LR versus ER, which is NaOH, which is basically what we just did in method two, is something that we do as a part of method one. So since I'm already done with this, so it would come easier to you to ratio 1, 8 into 10 raised to the power minus 3, ratio x, and you know x would be equal to 4 into 10 raised to the power minus 3 moles of H2SO4. Now that was one step. My bad. I'm gonna actually draw the line in a more appropriate way. And we need to go with, again, what we did in method two. So actually method two is the same as method one, 6 into 10 raised to the power minus 3. The total at the start of the question consumed is 4 into 10 raised to the power minus 3. And the answer would be 2 into 10 raised to the power minus 3 mole H2SO4 left unreacted. So actually the entirety of method number two comes as the second and third step of method number one. Okay. I should separate these parts. It's not difficult for us to understand what I was doing for method one as well as for method two. This would really clarify the whole. It looks like more like a mess than a clarification of the question. Okay, so for the students, for the starters, I always recommend method one. Method one is pretty simple and straightforward. First reactant with the product, second reactants ratio with the product. Whichever gives you a lower answer is the limiting reactant, whichever gives you a higher answer is the excess reactant. Now take the ratio of limiting and excess reactant to one another and find out the amount of excess reactant consumed. You already know the total amount of excess reactant in the first two parts of the question. So total minus consumed, what you just found out, subtract them and you'll get the left unreacted amount of excess reactant. That's what method number one is. Method two is that you put any reactant one and two side by side, and if your answer for the other reactant comes less than what you already had at the start of it, there you go. You've already found out that the reactant on the left is limiting reactant, the reactant on the right is excess reactant. You can easily take your answer, go for the subtraction, total minus consumed, and you can directly find the amount of excess excess reactant left unreacted. But if your answer comes out to be greater, the ratio would be otherwise, and you need to do the step again.
Sure. Uh, let's do it again. How so?
For example, if I was lucky enough that my reactant one was NaOH and reactant two was H2SO4, what if I started off with putting H2SO4 on the left and NaOH on the right? In that case, my answer wouldn't have give me the excess and the limiting reactant in the order they are now. They would have given me another order. So for that other order, I need to rearrange them on my left and right in order to get my answer right. That's what method two. There is a downside to method two as well, but even that downside gives you, with just one ratio, you can identify the limiting and the excess reactant. So I actually tend to refer to method two when you're only supposed to identify the limiting or excess reactant, since only one single ratio can do the trick. But if you need to go with the whole calculation and even find out the amount of excess reactant left unreacted, I insist you go with method one. But
Sir, I'll go with one.
both the methods can do everything for you. So it's really up to you which one do you opt.
Sir, method one would be more appropriate right now because this is I'm at a stage, I guess, where I need to get proper understanding of all the inner workings, which method one really gives, or provides, while method two is really direct right now. So I'll try method two when I'm more experienced with these questions.
Great. So let's go with method one. I'm going to send you the picture of this question. I'm going to post another
Sir,
question in the
before
form
that,
of a picture over here, and we can devise out the steps for you so that you can solve the question yourself. How about that?
could you just write the answers on questions just to make it more clear?
On the picture in the center? Is that what you're saying?
Sorry, yes, sir. Yes, sir.
Yeah, sure, no
Sorry.
problem. So if I use black, that would be for H2SO4, this is going to be 6 into 10 raised to power minus 3. Bad. Since we're writing exact answers, we need to go with three significant figures. That is 6.00 into 10 raised to power minus 3 mole over here. 8.00 in 10 raised to power minus 3 mole over here. Don't forget the three significant figure part. Reagent in excess, you can either write the name or the formula. So what I'm going to do is that I'm going to write the formula since it's easier. Most students do prefer the same thing. Writing sulfuric acid takes more time. Writing H2SO4 takes less. So that makes the perfect sense. The reason, since I tend to stick with the same reason every time. So total H2SO4 is equal to 6 into 10 raised to power minus 3 moles. That's what I prefer to do. Consumed H2SO4 is equal to 4 into 10 raised to power minus 3 moles, and excess would be equal to 2 into 10 raised to power minus 3 moles. So I tend to write my first step as my reason. And that's a great way of letting the examiner know that you understand every single step of the question. Because when you write the total, you tell the examiner you know how to calculate number of moles. When you write consumed, you let him know that he knew what exactly LR and ER is. because you can only find out the correct value of consumed when you have already identified the limiting reactant and the excess reactant. And finally, since you have already identified the limiting and excess reactant, you can of course calculate the amount of excess or something that has left unreacted at the end of the even at the end of the whole process, and that would be 2 into 10 raised to power minus 3 moles of H2SO4. So I love to write factual answers instead of just sentence-based explanations. Do you get the point?
Sir, I can't hear you. Your voice is totally.
Can you hear me now?
Hello, sir. Sir,
Can you hear me now?
your voice, completely was in. Yes, sir. Now it's audible.
Okay, if it's audible, let me repeat my answer. I was saying that I love to give some factual information as my answers instead of composing my answers based on sentences. So, since although there are just three simple mathematical facts or figures that I've quoted, but these figures are gonna give examiner the idea that I have a complete hold of the question. I have 100% understanding of what is going on with this question. You can write sentences. Your sentence was perfectly right, which you told me before, but I tend to go with the facts. Or if the facts can include figures, yeah, figures for it. But that's my way of answering. Your way of answering that you produced 4 into 10 raised to power minus 3 moles of Na2SO4, and that's why sodium hydroxide or NaOH is your limiting reactant, which definitely makes H2SO4 your excess reactant, is a very good answer. I'm fine with that answer. You can go ahead and write it and you'll get complete marks for it too. You'd see the same thing in the marking scheme. But I tend to write all the facts and figures, or at least the number of facts and figures that I can squeeze into the given space. So it's
Sir, the
really up
last
to you
question
which
I
one
have.
you're gonna pick.
Sir, I have another question related to this.
Sure,
Sir,
go ahead.
the third part is of mark one. Like there's only one mark for one answer. Would there be any chance where the reasoning could be 3 marks or 4 marks?
Reasoning can be a maximum of 2 marks in this question. It can't be 3 or 4 marks. Cambridge at least is not used to do that. I haven't seen in past 5 or 10 years papers, even more if I go back past 12 years, I haven't seen papers that the reasoning for limiting or excess reactant question has more than 2 marks.
Okay, sir. Understood.
All right. So can I send you the picture and we get ready for the second question?
Yes, sir.
Great. Reactant is in excess. And of course, the steps are already defined in a very good way. So we can try and do this question. Okay. Step by step, I'm going to explain this question to you so that you can solve every step of the way easily. This would also give you the idea how Cambridge tends to uh, manipulate the question in somewhat a more puzzling way to present it. So it's the same, these are the same things or same calculations that you are making every time, but the way the information is presented in front of you may sometimes become a little bit confusing or puzzling. Okay, so let's get started with it. So 6 grams of cobalt 2 carbonate, the formula for which is CuCH3, COCO3, was added to 40 cubic centimeter of hydrochloric acid. The concentration of hydrochloric acid was 2.0 moles per decimeter cube. Now calculate the maximum yield of cobalt 2 chloride 6 water, which actually forms in the second step, and show that cobalt 2 carbonate was in excess, that even these 6 grams were in excess. We actually required less than what we have. Now, he has already made a statement and we just need to prove it. In order to prove it, he has already laid out the steps which we are going to follow and find out some specific answers. So in order to find out the maximum yield or the maximum amount of product that we can form, the first thing we need to calculate is the number of moles of HCl used. Now for HCl, we have two pieces of information and that's pretty clear. The first one is the volume of HCl, which is given over here, 40 cubic centimeter. And the second one is the concentration, which is 2 mole per decimeter cube. So yeah, you have both the pieces of information. Go with the same formula that we applied in the previous question. Concentration is multiplied by volume, but volume is to be divided by 1,000 in order to get the answers in decimeter cube. So you would get your answer for number of moles used, right? So I think this should be easy, okay? So we are supposed to, I'm gonna just rearrange it a little bit. So I have the whole question in front of me. So that's what we are supposed to use in order to calculate the number of moles of this. This is 2.0 mole per decimeter cube multiplied by, was that 40? Wait a second. You see the value? Yeah, it's 40 cubic centimeter. So 40 cubic centimeter divided by 1,000. This cuts this. This is point and this is 0. I need to rewrite it. This is poorly written. This is point and this one 0. So yeah, what is this? I guess 8 into 10 raised to power minus 3 or 0.08. Yeah, 0.08, right? Is that correct?
Giving me 400 divided by 1,000 gives me 0.4.
Why 400? It's supposed to be multiplied by 2, not by 10. So 40 is being multiplied by 2.0, not 20.
Yes, sir, it's 0.08.
0.08. Great. Now, the number of moles of CuCl2 it is going to form. So here, we definitely need some ratio. So take a look at it. HCl, but in fact, I should not do it over here. So I'm going to solve this part over here. HCl ratio COCO3. So we have 2 ratio 1. So 0.08 ratio x, and x is equal to 0.08 divided by 2, which is 0.04. Is that correct?
Yes, sir, it's correct.
Great. So notice for this step, I'm going to solve it over here. COCO3 ratio CO, sorry, my bad. It's not COCO3. This is COCl2. So COCl2 ratio COCl2 6H2O. And this one I'm talking about the second equation. Take a look at this COCl2 here and this COCl2.6H2O. This comes over here. This is 1 ratio 1 to 0.04 means that this one is also 0.04. That's our answer, 0.04 moles. Since the numbers are same in the ratio, the answers would also be same. Is this step clear?
Yes, sir. Thought I was mute. Yes, sir.
Great. If this is clear, then let me
Because
tell you.
both of them are equal.
Right, both of them are equal. Perfect answer. So, the next thing, something that Cambridge has been manipulating as information. Relative molecular mass is something that we symbolize as MR. Now, MR is also equal to mass of 1 mole, and MR of CuCl2.6H2 is 238 grams. Instead of writing MR, they have been using the phrase mass of 1 mole in the old papers. You can say papers all the way from 2005 to 2018 have been using these phrases. Instead of saying the word relative molecular mass or molar mass, they have been using the phrase mass of 1 mole, means the same thing. Okay, so maximum yield would be what? This would be um, mass is equal to moles into MR. Now we know the moles are 0.04. We know the MR is 238. And this is something I can't do as mental math. So go ahead and let me know what the answer is for the multiplication of 0.04 and 238.
Sir, 9.52.
9.52 grams. Three significant figures. Perfect answer. So we had four fill in the blanks over here, and we had 4 marks, which means every step consisted of 1 mark, right? Now, to show that cobalt 2 carbonate was in excess, number of moles of HCl used, and we need to use the value from above. So the very first step was number of moles of HCl used. So I'm going to copy and paste the answer over here. 0.08 mole was our answer back from step 1. So I've simply copy and pasted the answer from here. And they've also mentioned use value from above. So since they are using another value again, they're not going to give you any marks for it. So remember, this step has no marks, which is an advantage for a student who has done it correctly, but the one who is going to be incorrect is going to be incorrect in both the spaces. Okay, so mass of 1 mole of CuCl3, and I have since explained it already. This is what MR stands for. So MR for CuCl3 is 119. So number of moles of CuCl3 in 6 grams would be what? So now we know moles is equal to, since he's asking for moles, so moles is equal to mass over MR. And he has just clarified for us that the mass is 6.0 grams and the MR is 119. So 6 divided by 119, of course, this is gram per mole. We cancel out gram and gram. What's the answer of 6 divided by 119?
The answer would be uh, 0,
0.
0.050.
0.050 mole. Now the question arises, how come CuCl3 is in excess? Now we have number of moles of both the reactants. Here well, what I do is that I use method 2. What you can do is that you can use method 1. Now for method 1, you've already made the calculations with respect to HCl. if you make calculations with respect of COCO3, you obviously know that they make more moles of COCl2. So remember, method 1 has two columns side by side. So if I go for method 1, so I have to go for HCl ratios CuCl2, and side by side, I have to go with the ratio of COCO3 ratio COCl2. Now this is 2:1, so that's why 0.08 gives me the answer of 0.04. And I've already calculated it previously in the second step of my question, so I'm not going to do it again. So this one is 1:1, so 0.05 is going to give me 0.05. So this tells me, and I'm going to change my colors over here. So this is a smaller answer, this is a bigger answer, this is less, these are more number of moles. So this one is our LR, and this one is our ER. Make sense? Method number 1, as in the very start of method number 1, I explained a simple rule, or the most important logic for method 1, that method 1 says that limiting reactant produces lesser number of moles of product. So if I compare it with my product, HCl is giving me lesser number of moles, 0.04, and our excess reactant, COCO3, is giving me more number of moles, 0.05. And I just proved it with method 1. So what would I write as my answer is that, and I can really write the comparisons over here, HCl produces, instead, I shouldn't be composing my answer in terms of limiting. I should be composing my answer in terms of excess. So CuCO3 produces 0.05 mole of COCl2, whereas HCl produces 0.04. So COCO3 is in excess. Sorry for my poor handwriting. I'm going a little out of space, but I am trying to put in all the pieces of fact
Hello?
in my
Hello?
answer. Can you hear me?
Yes, sir, I can hear you now. Sir, disconnected for a moment. Yes, sir. I understand most of this question, but I think I have to rewatch the recording again to really get the whole uh
Yep,
understanding of this.
that's all right. So right after we're done with this class, I'm going to send you the recording that would help you, specifically with the last two parts. I guess you need help with those.
Yes, sir.
Great, great. So if you don't have any more questions, can we wind up the class?